This lecture continues the basic problems associated with Gauss's law. As I mentioned in an earlier lecture, for highly symmetric charge configurations, using Gauss's law to quickly find the electric field associated with such configurations is rather straightforward. Primarily, the basic types of examples that you take a look at involve Gaussian surfaces that are spheres and cylinders. So I'm going to take a look at two applications of such with the following example. Okay, so please copy it down into your notes as I read it to you here. Here is first of all part A. We're going to use Gauss's law to find the electric field everywhere for the following. In part A, we have a sphere of uniformly distributed charge. The total charge is capital Q and the radius is capital R. So we're going to find the electric field everywhere in space for such a charge configuration. We're going to use a spherical Gaussian surface to do so. Okay, so let's take a look at our situation. All right, so here is a sphere of charge like so. It has a total charge Q associated with it and a radius of capital R associated with it. Now we're asked to set up and evaluate Gauss's law to find the electric field everywhere in space. We'll use a spherical Gaussian surface in order to do so. Okay, now of course Gauss's law is the following expression. And then what we'll do first of all is we'll set up a spherical Gaussian surface with a radius, small r, that is bigger than capital R. So then therefore the situation simply looks like this. We're going to set up our spherical Gaussian surface. Let me go ahead and just draw it here. Like so. This is our radius of the Gaussian surface, little r. And then the electric field associated with this spherical charge configuration, as long as it's a uniform distribution, is of course going to be radially outwards from the charge like so. I'm just going to draw here a couple of field lines like this. So then therefore, at all points on the surface, the magnitude of the electric field is going to be the same, and the dA vector is in the same direction as the electric field vector E. So then therefore, much like a point charge, we have the following. Here on the left-hand side, we're going to have E times 4 pi r squared. And then on the right-hand side, the Q enclosed is just going to be the entire capital Q, and then divided by epsilon naught. And then we divide by 4 pi r squared, and we end up with the electric field magnitude as being the following expression. Of course, this is the same as the electric field associated with a point charge. So this spherical distribution of charge behaves mathematically as a point charge as long as we are outside of the sphere. Okay, now let's go inside of the sphere. When we go inside of the sphere, the electric field lines are once again going to be radially outwards from the center of the distribution of charge, but the magnitude of that electric field is going to vary with distance from the center. I'm not going to draw the electric field. Instead, let's just draw the situation in the following manner. Okay, so now small r for our Gaussian surface is going to be less than big R. So here's the entire distribution of charge once again, Q and radius capital R. But now let me go ahead and draw in a Gaussian surface. I'll use a dotted line in this case, like so. And then right here is the radius of that Gaussian surface, small r. The left-hand side of the expression from Gauss's law is going to be exactly the same as it was before. However, on the right-hand side of the expression, what we have to come up with is a description of the Q enclosed. So how do we go about doing so? Well, we do so as a fraction. The charge density in this problem is uniform. It's a constant. So then therefore, I can think of the charge density, charge per volume, in the following way. I have, for example, right here in blue, the total charge divided by the total volume of this sphere. Q over 4/3 pi, capital R cubed. This is equal then, therefore, to the Q enclosed within my Gaussian surface, what I want, divided by the volume of this imaginary sphere. That is the volume of my Gaussian surface, which is 4/3 pi little r cubed. And now what I do is I solve for Q enclosed. The 4/3 pi cancels out, like so. Move the little r cubed up to the left-hand side to get Q enclosed by itself. So Q enclosed then therefore equals capital Q times little r cubed divided by big R cubed. So the Q enclosed, in other words, is a fraction of the total Q. That's the fraction that we then use. Okay, so now let's go ahead and write Gauss's law. Okay, I'm just going to do it from scratch here. Like so. So the left-hand side is once again just E times 4 pi little r squared. That's the surface area of our Gaussian surface there in green. This then equals the Q enclosed divided by epsilon naught. Like so. And now we cancel out an r squared here and here, and then therefore the electric field E has the following magnitude. Notice that the electric field obeys a linear relationship. As you get further and further away from the center of the sphere, the electric field magnitude increases linearly. Here's a way to check yourself at this point in the problem. The two equations, here for inside of the sphere and here for outside of the sphere, they should match each other at the sphere's surface. So let's see what happens when the radius of our Gaussian surface matches up with the radius of the sphere. Well, from this expression, the electric field would then therefore be the following at the surface of the sphere. It should be the exact same thing when we use this equation here. So when we use this equation here and set small r equal to big R, then you're going to end up with the exact same expression. So the two expressions match each other as they should at the surface. You have to be familiar with the graph associated with this problem. The graph of the electric field magnitude is a function of small r. It usually shows up on the AP Physics C exam as a multiple choice question. They'll present this problem to you, and then what they will ask you is to draw the electric field as a function of r, or at least identify the graph in the context of a multiple choice question. So let's go ahead and graph it out. So the electric field as a function of small r, let's set it right here as the surface of the sphere. So when we're inside the sphere, according to this equation, the electric field magnitude increases linearly. So when r is equal to 0, the electric field is equal to 0 at the exact center of the sphere, and it then increases linearly like so to this value right at the surface of the sphere. So right at the surface of the sphere, the electric field value is this quantity. Like so. Okay, and then when we go outside of the sphere, then the electric field decreases in accordance to the inverse square law, the 1 over r squared relationship. So then therefore the electric field begins to decrease according to 1 over r squared, like so. So in the context of a multiple choice question, they'll present to you this problem, a bunch of graphs, and they'll say, identify the correct graph. That's this one here. Okay, let me erase the board, then we'll take a look at part B. Part B is a cylindrical distribution of charge, once again of uniform charge density. Let me go ahead and erase everything. Okay, let me move my file. Okay, so now we have a cylindrical distribution of charge with volume density rho, that's charge per volume, radius capital R, and infinite length. So then therefore, for part B of the example, here's our cylindrical distribution of charge, like so. It has a radius capital R associated with it, it has a charge density, charge per volume rho, and it has an infinitely long length. Okay, what we're going to do is look to see what happens outside of the cylinder first. We'll set up a cylindrical Gaussian surface to do so, and then we'll set up a cylindrical Gaussian surface inside of the cylinder to see what happens for the electric field inside. Okay, so let's look outside first. So I'm going to set up a cylindrical Gaussian surface that has a radius small r that's greater than big R. So let me just draw it as a dotted line like so here in green. Here's our Gaussian surface. Like this. Right here is the radius small r. Now I will draw the electric field associated with this cylindrical distribution of charge outside of it. So then therefore it looks like this. And this then obviously illustrates why we use the cylindrical Gaussian surface to make this calculation, because at all points on the surface of this cylinder, the magnitude of the electric field is the same, and the dA vector points in the same direction as the black electric field vector E, like so. Okay, so then therefore, the left-hand side of the expression is going to be E, and then multiplied by the surface area of my green Gaussian surface. So then therefore, the surface area of a cylinder is 2 pi little r, which is the circumference of this circle, multiplied by the infinitely long length, like so. And then the right-hand side of the expression, how do you write the Q enclosed? Similarly to what we did when talking about the infinite line of charge. In this case, however, it's a cylindrical volume. So then therefore, the Q enclosed is going to be the charge per volume multiplied by the volume of my blue cylinder. What is the volume of a cylinder? It's the area of a circle, pi capital R squared, multiplied by the length L. And then divided by epsilon naught. Notice that the length L cancels. Like so. A pi cancels as well. Like so. And now we solve for E. So take the 2r and place it down to the denominator on the right-hand side. So I got rho capital R squared, and then divided by 2 epsilon naught times little r. So the electric field decreases as a 1 over r relationship as you get outside of the cylinder, just like it does for the infinite line of charge from an earlier problem. Okay, and now we'll go inside the cylinder. I'll do this on the bottom board. Okay, so here's the blue cylinder of charge, like so, of radius capital R. And now I'll set up a Gaussian surface inside, like so. My Gaussian surface here has a radius of little r. So then when I set up Gauss's law, the left-hand side of the expression is going to be exactly the same as it was before when I was outside of the cylinder. Remember that the left-hand side of the expression has to do with my Gaussian surface, which is here in green. So it's going to be E, and then multiplied by the surface area of my green Gaussian surface, circumference of the circle multiplied by the length. But then we have the Q enclosed on the other side of the expression. How do we get the Q enclosed? This is once again done in terms of density. So now think of the density, first of all, of the overall blue cylinder in the following manner. Density is equal to total charge divided by total volume. So it's going to be a total Q divided by a total volume. Pi r squared times L. But now, talk about density here in terms of this green Gaussian surface. Well, that's going to be equal now to the Q enclosed that we want, like so, but then divided by the volume of this green cylinder. That's going to be pi little r squared times L. And now what we do is we set the two equal to each other. Actually, we do so in the following way. What I'm going to do is, let's see, how do I want to do this actually? Actually, I just want to do this right here. Let's just solve for Q enclosed. So Q enclosed is equal to rho pi little r squared times L. That's what I want. I actually don't need this calculation here in order to get the Q enclosed. So it's this quantity here that goes on the right-hand side of the expression in the numerator. Okay, that's correct. So rho pi little r squared L, and then divided by epsilon naught, like so. So that's how you get the Q enclosed when you're talking about this green Gaussian surface. So density is charge over volume, like so, okay? All right, let's go ahead and simplify. So to do so, I'll cancel out an L here and here, cancel out an R here and here, cancel out a pi here and here, and then solve for E. So E is then equal to rho R over 2 epsilon naught. Notice that the electric field increases linearly as you move outwards from the center of this blue cylinder. The two equations should match each other at the surface of the cylinder. So when little r is equal to capital R, when you're at the surface of the cylinder, then E is equal to rho capital R over 2 epsilon naught. It should be the same thing here when little r is equal to capital R, and it is. So at the surface of the cylinder, you then have the following expression for the electric field magnitude. Like so. Okay, like part A of the problem with the spherical distribution of charge, here you also have to be familiar with the graph of the electric field magnitude as a function of small r. For now, this cylindrical distribution of charge. So that graph looks like this. So over inside, the electric field increases linearly like so to this value here at the surface. So let's say right here is the surface of the cylinder. And then we increase linearly to that value. So right over here is the value of the electric field at the surface. That's this quantity here. And then when we're outside, it decreases as a 1 over r relationship, like so, as opposed to 1 over r squared when talking about the spherical distribution of charge. So these are two nice, easy examples that everybody has to be familiar with, involving these highly symmetric charge configurations, spheres, and cylinders.